Now I'm working on the next IQ video, which hopefully is up in a couple of days, but I can't really guarantee anything. I have an exam that I am studying for, and I also have a couple of days of working as a substitute teacher coming up. So yeah, I'm working on it, but I'm gonna try and finish that IQ video as soon as possible. Anyway, I thought I would make this video as it's pretty quick, and it's gonna be responding to a flat earther. Just get a load of this guy.
The Earth isn't flat. And by the way, this is called gravity.
See, the thing is, this video has hundreds of thousands of views and not as many dislikes as I would like, to be honest. And seriously, this is this guy's argument. Neil deGrasse Tyson displays what gravity is by displaying that an object will fall, and somehow defying the force of gravity by jumping disproves gravity? Well, it doesn't, because you fall back down, don't you? Right, here's the thing. As you're jumping upwards, you will notice that your initial velocity upwards is quite high, but it decreases the sooner to the top you get, and eventually you reach a point where your speed not just reaches zero and you stop, but it will actually become negative, which is why you return back to Earth. You see, gravity is not some kind of force that just stops existing as soon as you reach the ground, though. It's always working on you, which is why you require energy to even be able to jump upwards in the first place. You see, the small letter g in physics stands for the small gravitational constant acceleration, which is about 9.82 meters per second squared. Although it is a bit less right at the equator. I believe it's somewhere around 9.78 meters per second squared. Now, the reason we know that gravity exists is because, like I mentioned before, as you're jumping upwards, you will return back down to the ground. It is a force that's constantly working on you. If you need to put in energy into a spatial vector that is opposite of the direction you're naturally heading, then that means that you need to overcome a force in that direction. For instance, let's say that you're in an elevator, and the elevator is out in space. Now let's say that the elevator at first is stationary, which means that you're pretty much weightless in there, you're floating around. But as the elevator is slowly accelerating, you're gonna slam into its floor, and as it is continually accelerating, let's say, for the sake of argument, at 9.82 meters per second squared, you will be able to stand on the floor of that elevator. In fact, if you can't look outside and see that you're in space, you might as well believe that you're in an elevator on Earth. Because the force in the vector that you're traveling is the same as gravity. Now you might be wondering,
but Sandre, what exactly is the vector of gravity on Earth? I mean, in the elevator it's very easy to understand because, you accelerate in one direction. So in this image there's really only one dimension to think about. But on Earth, I mean, it doesn't really work, does it?
No, exactly. Which is one of the reasons why we know the Earth is round. Look, wherever you are on Earth, the gravity constant acceleration is pretty much consistent. It only varies very, very slightly. It's practically speaking identical across the world. So whether you're at the equator or one of the poles on Earth, you will fall back down to the ground at about 9.8 meters per second squared. You can easily do an experiment and verify this acceleration constant yourself. Just make sure you don't use something like a feather, because then aerodynamics will slow down its fall. You can use the following equations to easily calculate the small g. Now, since gravity is pretty much constant wherever you are on Earth, this tells us something. The Earth has to be round. Why, you may ask? Well, because we know that mass exerts gravity. Gravity originates from mass. Gravity, however, is a very weak force compared to electromagnetism, the weak nuclear force, and the strong nuclear force. And the only reason that the gravitational constant of acceleration is as high as it is on Earth is because we have a very dense and massive iron core. Also naturally that the Earth is so fucking huge. Now, if we were to live on a flat Earth, you would have a problem. Where exactly is the mass on this flat Earth to give such a high gravitational constant of acceleration? If you were to argue that the gravitational pull originates from a dense mass at the center of this flat Earth, this doesn't really work. Because, well, gravity would be weird on this planet. You see, if gravity were to be divided across the mass of this flat Earth, the gravity vectors would look something like this. As soon as you were to try and move away from the center of this flat Earth, you would notice that the vector of the force of gravity would change at an angle. This angle would become more and more severe as you were to move out. Eventually you would get to a point where, well, you wouldn't be able to stand because you would be dragged along the ground back to the center. Now, nowhere on Earth do we ever notice that the vector of gravitational pull has an angle that isn't 180 degrees relative to the ground. Meaning that wherever you are on Earth, the gravitational vector will always be relative to you straight down, so to speak. Or 180 degrees from the center of the sky above you. You can be away in Japan, or in Italy, or in Greenland, and never once will this not be true. Meaning that in order for this to make sense, the Earth has to be a sphere. This is the only way to explain that the gravity vector, regardless of where you are on Earth, is always 180 degrees relative to the ground and the sky's dead center. The ironic thing, however, of course, is that if the Earth was indeed flat, not only would you notice that the gravity vector would change its angle relative to the center of the flat Earth as you were to move further out, but because of the nature of gravity, the Earth would naturally over time become a sphere, as this would be the most efficient spreading of the vectors of gravitational pull. Now, isn't that just some sweet-ass irony? This doesn't prove anything. I mean, anyone who's read basic high school physics should be able to, with some simple formula, show why you're observing what you're observing. It is true that the magnet is powerful enough to overcome gravity on those paper clips, but not on everything else. After all, you can stand under a magnet and you're not going anywhere, are you? Unlike something made out of iron, let's say. Like I said before, electromagnetism is way stronger than gravity as a force. But it only works for certain materials, usually metals. And even then, once something becomes massive enough, i.e. has enough mass, the gravitational pull of the Earth will overcome that magnet. After all, if you have enough mass gathered in one place, that gravitational pull, even though gravity is the weakest of all forces, will become so strong that all the other forces nearby won't be able to do shit. Let's take a neutron star, for instance. It is an entire star, usually the size of a big city, but has the same density as an atomic nucleus. So in a way, I guess you can say that a neutron star is just one big atomic nucleus of sorts. Not really, but kinda. And the gravitational pull of a neutron star is just ridiculous, simply because you have so much mass in such a small space. There is something in the universe that has an even stronger gravitational pull, however, and that's the black hole. They are so strong that time and space itself bends around them. In fact, as soon as you get across the so-called event horizon of a black hole, all known laws of physics break down. Yes, that's how strong the force of gravity is in these things. But again, just to summarize, the reason that you can lift something such as a paperclip with a magnet, is because the magnet, even though compared to all of the Earth, has a force that is way stronger than gravity, proportionally speaking. The Earth, however, since it is so massive and big, has a gravitational pull that will be able to overcome any other force if that thing that you want to lift has enough mass. And again, whatever you want to lift usually has to be made out of metal, such as iron. Alright, so I want you to imagine that you blow up a beach ball, and then you try to push that beach ball under a body of water. You will find it very difficult. The reason is, the air inside the ball has less density than the water surrounding the ball. It's kind of the same principle when you blow up a balloon with helium, or something that's even lighter, hydrogen, and that balloon that's filled with this very light elemental gas is surrounded by the air. Since helium, or hydrogen, has way less mass per atom than the nitrogen and oxygen that you find mostly in the air, the local density of the gases around the balloon will increase the closer it gets to the Earth's surface, again due to gravitational pull. Now, since the density is low enough of the gas in the balloon, density simply being mass per volume, this will naturally lead to the balloon floating, if you will, up to the surface of our atmosphere, much like the beach ball will float up to the surface of the water. This really isn't difficult to understand, and in fact, the only way to explain this phenomena is with gravity. You haven't disproven gravity here, you've actually proven it, you dumb fuck. Alright, I'm not going to bother too much with giving a deep explanation on this one, but here's a summarized version. Basically, you have a natural tension of this spring. A slinky is essentially a spring. Now, as you're holding the slinky like that and you let go, the natural tension of the slinky is going to equal that of gravity at the very bottom of the slinky, giving the illusion that a part of the slinky isn't falling. In fact, it is. It's just counteracted by the natural tension, until this tension is no more, and eventually all of the slinky will fall down. Again, this isn't very hard to understand. In fact, understanding how something like a spring works is quite fundamental to any physics class, even very basic ones in junior high.